Have you ever really stopped to think about how all the devices around us actually work? I mean, everything, from your thermostat to a car engine. Well, deep inside every single one of them, there's a tiny brain, a microcontroller. Today, we're going to pull back the curtain and see how engineers go from just an idea to a fully working electronic system. Okay, let's jump right in.
Here's the game plan. We're going to start with the absolute basics, the blueprint for any electronic device. Then, we'll build a general-purpose system to see it all in action. After that, we'll look at what happens when you need more memory. And then, we'll apply everything to a real-world project. And finally, we'll see how engineers pick the perfect little brain for any job.
All right, first up, the blueprint. You see, designing a complex system isn't some kind of magic. It's a very structured, very logical process. Every great device, and I mean everything, from your coffee maker to your phone, it all starts with a really solid plan.
So, that leads us to the big question, right? How do you actually do it? How do you go from a completely blank page to a piece of hardware that actually works?
Well, it really boils down to this clear three-step process. First, you have to define exactly what the system is supposed to do. Then, and this part is absolutely crucial, you draw a block diagram. Think of it as a super high-level map of your system. And only after that do you dive into the nitty-gritty of the detailed circuit schematic.
And this right here is the real secret sauce, the block diagram. It's the master plan, the architectural blueprint. It deliberately ignores all the tiny, complicated details to focus on the big picture. What are the main parts? How do they talk to each other? It is the absolute key to taming complexity before you get totally lost in the weeds.
Okay, so theory is great, but let's see how this blueprint actually works in practice. We're going to look at a general-purpose-based system that's built around a really popular microcontroller, the PIC16F877. This is going to be our hands-on example to see where theory meets reality.
And there it is. This is the block diagram for our system. See how clean and simple that is? Right in the center, you've got the MCU, our brain. And it's just connected to some inputs, like a keypad, and some outputs, like a display, plus some memory. This simple drawing is where every single design starts.
And then there's this. This is what that simple plan looks like in the real world. Whoa! I know, right? It looks incredibly complicated, kind of like a huge city map with a million tiny streets. But, and this is the important part, don't worry. Every single piece of this detailed schematic connects right back to one of those simple blocks we just looked at.
So how in the world do you even start to read this thing? Well, you tackle it one block at a time. So somewhere in that maze is the clock circuit. That's the system's heartbeat, ticking away millions of times a second. Then you've got the connections for the LCD display, which is cleverly wired up to save some of the microcontroller's precious pins. But here's what the block diagram didn't show us: all the support systems. You see, this schematic also includes stuff like power regulation to make sure the brain gets clean, stable voltage, and even a special chip that lets the whole system talk to a computer. Every single one of these functions has its own little neighborhood on this big city map. It's complex for sure, but it's not random. It's a system of systems.
Okay, so we've got our base system, but what happens when you hit a wall? A really common problem in system design is just plain running out of memory. So let's take a look at how we expand the system's capabilities when that happens.
And the choice really comes down to a classic engineering trade-off. On one hand, you have serial memory. It's simple. It uses very few connection pins, but it's slow because it sends data just one bit at a time. On the other hand, parallel memory is way faster. It sends 8 bits at once, but it absolutely eats up your valuable I/O pins.
And this schematic shows you what you have to do when you need that extra speed. You see, to add faster parallel memory, the circuit just gets more complex. You need the memory chips themselves, of course, but you also need extra helper parts, like an address latch and a decoder, just to manage all the data traffic. It's a perfect example of adding a bit of complexity to gain a whole lot of performance.
All right, so we've seen the building blocks, and we know how to expand them. Now, let's put all this theory into practice. We're going to use these exact same principles, from the initial idea, to the block diagram, to the final schematic, to design a real-world device, a temperature controller for a refrigerated shipping container. And this is our starting point, the specification. It's our mission statement. It tells us exactly what we need to achieve. Keep the temperature in a very specific range, let the user change it, show them the temperature, and sound an alarm if anything goes wrong. Every single design decision we make from here on out flows directly from these requirements.
So what's the very first step? You guessed it,
We draw a block diagram. Here, our MCU brain is connected to temperature sensors, some up and down buttons, a display, and a relay that's going to switch that big, powerful compressor on and off. Once again, we have a simple, elegant plan for what is actually a pretty critical system.
Now for the fun part, picking the actual components based on our spec. For the brain, we chose the PIC 16F818. Why? Because it has 5 analog inputs, more than enough for our sensors, and it has an internal oscillator, which means we don't need an external crystal. That makes the whole design tougher, especially in a vibrating truck. And speaking of sensors, why 4 of them? Redundancy. This is mission-critical stuff. If one sensor fails in the middle of the ocean, the system can use the others to keep working and save thousands of dollars of cargo. The display has to be a big, bright LED that a driver can see at a glance, day or night. And the whole thing gets put in a rugged, moisture-proof box. See how every single choice isn't just random? It all ties back to solving real-world problems.
And here it is, a look at the final design concept. You can see the main controller unit, the remote alarm for the driver's cab, and those separate sensor units. We've gone all the way from a simple text document to a block diagram and finally to a complete, thought-out physical system. Pretty cool.
Now, we've only looked at a couple of specific microcontrollers, but there are literally thousands of options out there. So how on earth do engineers choose the right brain for the job?
Well, when an engineer sits down to make this choice, what's going through their head? It really just boils down to 3 main things. First, how many I/O pins does it need? How many connections to the outside world? Second, memory size. How much room does it need for its instructions and its data? And third, what kind of built-in hardware or peripherals does it have? Those can save you a ton of extra work.
And this table really gives you a feel for the incredible range of options. You might have a tiny 8-pin chip that's perfect for a simple little flashing toy. Then there's our 40-pin chip from earlier, the 16F877A, which is a great all-rounder for learning. But then, for really complex job, like a car's engine management system, you might need an 80-pin beast with a massive amount of memory. It's all about picking the right tool for the job. Not too little, not too much.
And believe me, these tiny brains are everywhere. And I mean everywhere. In fact, the average modern car has more than 50 of them, each one quietly controlling a different little system.
Which kind of leaves me with one final thought. From the device you're watching this on right now, to the lights in your room, to the thermostat on the wall, these little electronic brains are silently running our entire world. Makes you wonder, doesn't it? How many do you think are helping you right this second?